Let's try and understand optics now. In case of optics, we have learned about glass slab. Incident ray passes through glass slab, and as it enters the glass slab, the ray of light bends towards the normal, air being less denser than glass. So we have learned that rays of light always bends towards normal when it travels from rarer to denser medium. Alright, that's what we are observing over here. Alright, now this is the angle of incidence. This is called as glancing angle. This is called as angle of refraction. And in case the ray goes undeviated, as I've shown in pencil, this angle between refracted ray and the undeviated ray is called as angle of deviation. Alright, so 1, 2, 3, 4 angles we learned. Now let's get into formula. Now how do we mention it? Now see, this is the symbol for refractive index. Incident medium comes at the top and refraction medium comes at the base. So this is how we signify. So obviously the angle of incidence would be here. Now for example, in this case, one is air. So it has to be AG, air to glass, and the angle of incidence is in air, obviously. Alright, so let's get into this part of it now. Now, this is mu2 over mu1. Mu2 over mu1. How to keep in mind? Though it is at the base, but it comes at numerator. Mu2 comes at the numerator. Okay, now formula for mu is C over V is the formula. So for mu2, it would be C over V2. And for this, it would be C over V1. Now what is C and what is V? C is velocity of light. Alright, in vacuum. Alright, whereas this is velocity of light in medium. Now in this case, it is medium 2, and in this case, it is medium 1. So obviously, this would get C gets cancelled, and what we get is V1 over V2. Formula for V is N lambda. So for V1, it would be N lambda 1. Lambda we know is wavelength. Lambda 1, N lambda 2. Alright, now why do we have N both? In both the mediums. In both the mediums, we have N. Now what is N? N is frequency. The frequency does not change in medium. It is irrespective of medium. So N gets cancelled and we are end up with lambda 1, lambda 2. It doesn't stop here. Now also we have Snell's law, which says sine I over sine R. I comes here, sine I over sine R. And furthermore, it's d2 over d1, delta 2 over delta 1. This is angle of deviation. This we would be dealing when I'm talking about prism, but you have got to keep it in mind. This entire stuff we have got to keep it in mind, because see, what I've done is I've tried to put in lots of formulae into one equation itself. Like for example, you get the formula for mu, which is C over V. You get the formula for V, which is N over lambda. You also end up with relationship like lambda 1 and delta 1, inversely proportional. Alright. Velocity and lambda directly proportional, and so on and so forth. Alright. So this would be of a great significance. Alright. Now let's move into next aspect. Let's understand the theory of real depth and apparent depth. Imagine a crane flying over a pond, and there's a fish. There are lots of fishes, but I am concerned with one fish. Okay, there's a fish in the pond. Now this fish, the actual depth of fish from crane is this. So this is a real height of crane to fish. But since there is change in refractive index, rarer medium, denser medium, the crane finds fish elevated. Alright, so this becomes the apparent height. So crane is finding fish over here, but actually the fish is over here. So this becomes the real height and this becomes the apparent height. Now, there is a formula which correlates real height and apparent height. So, refractive index air to water is real height upon apparent height. Alright, so if now we talk in terms of fish, obviously it would be toppled. The equation would be toppled. Alright, occasionally we also find numericals based on this formula. Okay, let us get into total internal reflection. There are lots of things which are concerned with total internal reflection. It's like the prism, binocular prism, the periscope, optic fiber that we use. These are synthetic, whereas in nature we see mirage. Mirage is also result of total internal reflection. Rainbow that we see, it's also effect of total internal reflection. So let's understand how does it work. Now see, there's a coin here in this, it's water. Now what I do is I observe the coin from top of it. Alright, now since I'm observing it from top of it, so I would find coin elevated to this place. Alright, so obviously now if I am here, this becomes the apparent height and this becomes the real height. The theory which we talked before. So theory of real and apparent would come into picture over here because we are seeing it straight like this. Okay, now what happens if I observe the coin from here? If I observe the coin from here, I would find it somewhere here, not here. Alright, then again suppose I bend my eyes on the surface of water, I would find coin somewhere here on this surface. Alright, and suppose now I place myself here and observe it, then I'll find the coin at the top floating on the surface. Alright, now let's get into depth. Now see, this is the coin, so this is the source of incidence. So incident light comes from there and passes out from denser to rarer medium. So this is angle of incidence and this is angle of refraction. Obviously this is the normal. Obviously this being normal. Now that was when I was observing the coin from here. Now when I observe the coin from here, what happens? So this is the incident ray, this is the angle of incidence, and this is the angle of refraction, and this is the ray of refraction. So I find the coin over here on the surface. Now when I go further down there, what happens? This is the angle of incidence now, and this is the angle of refraction. But that angle of refraction is so high that it is reflected in water. Alright, so what's happening? As I keep on moving from here to here to here to here, angle of incidence, if you observe, keeps on increasing. This angle of incidence is greater than this angle of incidence, and this angle of incidence is greater than this angle of incidence. When I come here, what happens? The incident ray coming from there is on this surface. So what is the angle of refraction? Angle of refraction is 90 degree. When I further bend down, what happens to angle of incidence? Now the angle of incidence becomes greater than critical angle, owing to which it is being reflected back in water. So what do we conclude from this? We conclude whenever a situation is there where angle of incidence is greater than angle of critical angle, then the rays get reflected in the same medium. It does not pass through to another medium. Alright, so this is what is called as total internal reflection. Total internal reflection. Now let's get into the formula. The refractive index, water to air. water to air. This is our source of incidence. So water to air. Snell's law, sin I over sin R. Now we are talking about this. All right. So sin IC. So this was sin IC, whereas sin R was 90. So I put in sin R as sin 90. Now we know sin 90 is 1. So W mu A becomes sin IC. Or suppose if I want to put it in terms of A mu W, air to water. This was for water to air. This was from water to air, sin IC. But if I want to make it for air to water, it would be obviously reciprocal, 1 over sin IC. So this is the formula that you have got to keep in mind for critical angle. Mind you, it is for air to water. First and foremost requirement for total internal reflection is that ray of light has to pass from denser medium to rarer medium. And the second requirement is the angle of incidence has to be greater than critical angle. Alright. So these are two requirements for total internal reflection. Now roughly I have just tried to show over here how the theory of total internal reflection works in all three cases. Now in this case, this is the optic fiber. We have in the center, we have core and at the surface in the center we have core, and at the surface we have clad. Refractive index of core is 1.7, whereas that of clad is 1.5. So denser to rarer medium, so the rays of light keeps on reflecting. Total internal reflection. Then again, if we talk in terms of prism binocular, this is a prism, rays falling this way, rays incident like this. Now it falls here and it gets reflected. Why? Because if you draw normal over here, this angle becomes 45 degree. So angle of incidence becomes 45 degree and critical angle is approximately 42 degree for prism. So this angle is greater than 42 degree. So total internal reflection. Now same way if we go to mirage. Now even in periscope also same is the story. You have two prisms there and it's all because of effect of total internal reflection that we see. Mirage is also the same story. In mirage what happens is, now suppose we are in desert. Now desert air is very hot. So at this surface air is very hot. Above that it is slightly cool. Above that it is cooler, coolest. Alright. So with heat we also know depends density. So least dense, denser, densest, if we just assume these three layers. So obviously the condition required for total internal reflection is quite okay. So it's passing from denser medium, then again it is from denser to lighter. So that's what we observe. So angle of incidence keeps on, as we saw here, angle of incidence keeps on increasing, the angle of incidence keeps on increasing, and when it comes to this surface, the angle of incidence becomes greater than critical angle. So total internal reflection occurs and then it comes back and we see whatever the object was, its image we see here. Alright, so this is the theory of mirage. And obviously even for rainbow the story goes on same line, but along with that also comes dispersion, which I would be picking up after prism.